Students, now we will see application of Euclid's division lemma. Here is the first question. Find the HCF of 81 and 237 using Euclid's division lemma. So we start with the larger integer 237 and use Euclid's lemma to get the following equations. To get the equations, we divide 237 by 81, the bigger number divided by the smaller number. So it will be 81 2s are 2 1s are 2 and 2 8s are 16, and subtract this, and so the remainder will be 75. So as we have seen in the previous episode, this can be written as 237, which is equal to 81 into 2 plus 75. Now here, since the remainder is not 0, this is the remainder and this remainder is not 0, so we will still solve it further till we get the remainder 0. So here we will divide 81 by 75. So if you divide 81 by 75, we will get 75 ones are 75, so it will be 6. So remainder is 6, and this can be written as 81, which is equal to 75 into 1 plus remainder 6. Still here we have not got remainder as 0. So we will proceed again, divide 75 by 6. So it will be 75 by 6. So it will be 6 1s are 6, 1 take down 5, 6 2s are 12, and so 15 minus 12, that will be 3. So 3 will be the remainder, and this we will write as 75, which is equal to 12 into 6 into 12 plus remainder 3. Again the remainder is not equal to 0, and so we will divide 6 by 3. So 6 divided by 3, it will be 2 3s are 2, 3 2s are 6, and so it will be 0. Now here we have got remainder as 0, so it will be written as 6 is equal to 3 into 2 plus remainder 0. And since we have got the remainder as 0, we can see that the HCF of the given numbers is 3. So the required HCF is equal to 3. Take the another question. Find the HCF using Euclid's division lemma of the numbers 135 and 225. So we start with the larger integer, that is 225. So it will be 225 divided by 135. So it will be 135 ones are 135. We subtract this, and therefore the remainder will be 90. So we write this as 225 is equal to 135 into 1 plus 90. Since the remainder is not equal to 0, we will solve it further, and we will take 135 and divide it by 90. So it will be 135 divided by 90. So it will be again 90 ones are 90, and so the remainder will be 45. So this will be written as 135, which is equal to 90 into 1 plus 45. Again the remainder is not equal to 0. We will divide 90 by 45. So it will be 90 divided by 45. 45 2s are 90, so remainder will be 0. So we write this as 90 is equal to 42 into 2 plus 0, and since remainder is equal to 0, we say that 42 is the HCF of the given number, and therefore HCF of 135 and 225, that is equal to 45. Sorry, this should be 45 into 2 plus 0, and so the HCF is 45. Now let us see another question. Use Euclid's division algorithm to find HCF of 867 and 255. We start with the bigger number, that is 867 divided by 255. So it will be 3s are 765. So if you subtract this, it will be 102. So this can be written as 167, which is equal to 255 into 3 plus 102. Since the remainder is not equal to 0, we will solve it further. 255 divided by 102, so it will be 255 divided by 102, so it will be 102 2s are 204, and so the remainder will be 51. So we write this as 255, which is equal to 102 multiplied by 2 plus 51. Here again the remainder is not equal to 0, so divide 102 by 51. So 102 by 51 will be 151 2s are 102, so the remainder will be 0. So this we write as 102 is equal to 51 into 2 plus 0, and since the remainder is equal to 0, the required HCF will be 51, and therefore the HCF of 167 and 255, that is equal to 51. Another question is find the greatest number that will divide 445, 572 and 699, leaving the remainders 4, 5 and 6 respectively. The given remainders are 4, 5 and 6, and the three numbers are 445, 572 and 699, and therefore the required greatest number will be the HCF of 445 minus 4, that is equal to 441, and 572 minus 5, that will be equal to 567, and 699 minus 6, that is equal to 693, and therefore HCF of all these three numbers will be the required greatest number. So we will find the HCF of these three numbers. So first we will take the two numbers 441 and 567. So divide 567 by 441. So it will be 441 ones are 441. So the remainder will be 126. So this we will write as 567 is equal to 441 plus, multiplied by 1 plus 126. Again the remainder is not 0, we will still solve it further. So 444 divided by 126, so 441 divided by 126, so it will be 126 3s are 378. So if you subtract this, you will get it 63. So this will be written as 441, which is equal to 126 into 3, which is equal, sorry, plus 63. Again the remainder is not 0, and therefore we will divide 126 by 63. So 126 divided by 63, so it will be 163 2s are 126. So subtracting we get the remainder 0. So it is 126 is equal to 63 into 2 plus 0, and since the remainder is 0, the required HCF will be 63. And so the HCF of the two numbers 441 and 567, that will be 63. Now we will find the HCF of 693, this third number 693, and the LCM of the remaining two numbers, that is 63. So divide 693 divided by 63, so that will be equal to 11s are 693, so remainder will be 0. So it is written as 693 is equal to 63 into 11 plus 0, and therefore the remainder is 0, so the HCF will be 63. And since the HCF of 441, 567 and 693, that is equal to 63, and therefore the required greatest number, that is equal to 63. The another question is, show that every positive integer, even integer, is of the form 2q, and that every positive odd integer is the form 2q plus 1, where q is some integer. Suppose a is any positive integer. Suppose a is any positive integer and b is equal to 2, then by Euclid's algorithm, we have a is equal to 2q plus r, where 0 is less than or equal to r and r is less than 2, because b is 2. It means what? R is equal to 0 and r is greater than 0 but less than 2, and therefore r can be equal to 0 or 1. So if r is equal to 0, so when r is equal to 0, this will be 0, and so we will get a is equal to 2q, and when r is equal to 1, we will get a is equal to 2q plus 1, and if a is of the form 2q, then a is an even integer. Then a is an even integer, and any positive odd integer is either of the form, and any positive integer is of either of the form 2q plus 1 for some integer q, for some integer q. Now the next question is, show that any positive integer is of the form 3q, 3q plus 1 or 3q plus 2 for some integer q. Suppose a is any positive integer. Suppose a is any positive integer and b is equal to 3 and b is equal to 3, then by Euclid's algorithm we have a is equal to 3q plus r, where 0 is less than or equal to r is less than 3. It means r will be equal to 0 because r is equal to 0, or r is greater than 0 but less than 3. It means r can be 1 or 2 also. So when r is equal to 0, this will be a is equal to 3q because r is 0, and when r is equal to 1, a will be equal to 3q plus 1, and when r is equal to 2, a is equal to 3q plus 2, and therefore thus any positive integer is of the form of 3q or 3q plus 1 or 3q plus